pleasure to introduce him now. And he's going to speak about mass-stationarity through the Cox process. So, let's start.
Thank you. I'm sorry for squeezing in this talk so late in the day also. Can you hear me? So this is a topic I've been thinking about on and off for 30 years, I guess. And some of you have heard me talk about it on and off for the last 20 years. And so what is new now? What I'm going to the new thing is the Cox process. How do I do this? Where is the light? Okay, there it is. Okay. So what is the sort of main topic? It's the question of what it means to say that a location is typical, or time is a typical time for a stochastic process or a random field. And for instance, if we have a few points scattered somehow on maybe at random, or maybe deterministically on the circle, I'm taking the circle just as a nice example. Then if we place the origin on the circle at random uniformly, then it's a typical location on the circle, in the sense that if you move somewhere else, the pattern of points will have the same distribution.
The points are fixed and are not
They can be random or fixed or whatever. It's just so I'm saying if we have some set of points, say random or non-random, and you pick the origin uniformly on the circle, then this location is typical in the sense that if you move to another location, for instance 30 degrees in this direction, the pattern of points will be the same, have the same distribution. Another way of choosing a location, choosing the origin, is to choose one of the points as the origin. So say we chose this one. Well, this is not a typical location on the circle, because if you now shift for 30 degrees, for instance, then you will typically not end on a point. But it's this location, if we pick this point uniformly among the points, it's a typical location, it's a typical point on the circle, in the sense that if you move to the next one on the right, you have the same distribution of the point pattern. And now we could, rather than having these points, we could have some mass distribution, a diffuse mass distribution on the circle. Maybe there is no mass here and no mass here. Then we could do the same. We could pick the origin at random on the circle, for instance there, and the things look the same. It's a typical location on the circle in the sense that it's invariant under rotation. But if you now choose the origin according to this mass distribution, then, for instance, you could not end here. You would have to be somewhere where there is mass. Say we ended here. And then, if we choose the origin according to this mass distribution, say this is a probability distribution, then this location is typical in the mass, in some sense. So this is the kind of typicality I'm going to talk about, and recently I started working with Gunther Last, and we moved from earlier I've been considering only point processes, simple point processes, but now we are in a situation like this one where there is general measure, general random measure. So if we, rather than considering a compact situation like here, if we, for instance, consider the line and what does then, and there is, say there is countable infinite number of points on the line. What then does it mean that the origin, say the origin is here, is a typical location for this point pattern? Well, suppose this point pattern is a point process, simple point process, then obviously we would like it to be stationary, because then if we shift to a t here, the distribution wouldn't change, and it's natural to say that the origin is a typical location in the point process. Now for simplicity, consider the Poisson process in one dimension. So this is the Poisson process. Then you know that the intervals here are all exponential. They are IID and exponential. Except this interval here, the one from this point to that point, it's actually split into two independent exponentials, and therefore if we add an extra point here, we need to add an extra point to get all the intervals IID, exponential, and if we are standing here and we move to the next point on the right, we will still have IID exponential intervals, so things look the same from here as they did from here. And so it's natural for this process to say that it is the origin, the point at the origin is a typical point of the Poisson process. This can be formalized in a simple way, that if you shift to the next point on the right or to the nth point on the right, the distribution of the point pattern doesn't change, and the same happens if you go backward. So how does this idea of the origin being a typical location in a mass distribution extend to general random measures? What happened now? Page down. How do I get a new page? No, that's not what I wanted. L. Okay. What is happening now? Control L. Where is Control L? No, that's not what I wanted. How do I get back? Escape. Oh, so I can't just take one page at a time. Okay, sorry for that.
Scroll down a little bit.
Yes, it's stupid. So this is what I need to do. Okay.
You don't need this point, no? You don't need this point.
I might need it. but we can discuss it when it comes.
There is a mechanical one, you know, you can use.
Oh, where? Oh, there is a mecha. Thank you. Okay, so we now have psi is a random measure on a locally compact second countable abelian group, and let's think about RD. And actually, I'm going to discuss this in where is the cleaner?
Down.
Below your laptop.
Here. I'm leaving some white here because I want to have a mass distribution on the blackboard. So this is psi. It's mass distributed some random way in space. And so now let's take G to be just R2. And so we have some random measure. And in addition to this random measure, we can have some random element, X, on which the group acts. So this random element could simply be a random field, so that at each location here we'd have some value out in the third dimension. That's the typical example. I like to think of this as the Brownian sheet, and this would be the local time at 0. That's a rather fancy example, but it's it actually fits into this. Okay. Okay, stationarity is defined. Here is the pointer. Is defined this way. So if I apply gamma to this pair, it means, what does it mean? Well, the origin is somewhere. The origin is somewhere, and gamma is somewhere else. And if I shift the origin to gamma, then the distribution, that's what this thing here means, then the distribution doesn't change. That's stationarity. Okay, so I like to think of stationarity as meaning that the origin is a typical location in the group. Okay, so now comes mass stationarity. It has a fancy definition that sort of looks rather mysterious, and that's a little painful, but it's actually rather nice if you think about what it's saying, but it's not very transparent. So the pair X psi is mass stationary if the following holds. We take here is X and psi, these guys here. Then we take a uniform random variable on, which is uniform on a relatively compact Borel subset of G. And we also take another random variable which has the condition, given this triple here, the conditional distribution of V is the mass distribution of psi on the set C minus U, conditionally on that set. So what does this mean? I brought this set C with me here. It's here somewhere. Here it is. Take a rectangle. So U is, this is the set C, and you pick some uniform random point, random location in the set, for instance here. And so actually I should have said that the origin is actually assumed to be in the support of psi. So there is a mass around the origin. So take this set here, see? There it is. And this is the vector UC. And now you see there is this, in this set here now there is some mass, at least this mass around the origin, and then some mass somewhere else possibly. Pick a location in this mass according to the mass distribution. So for instance, there. So now if we move the origin from here to there, this is the vector VC. If we move the origin from here to there, nothing changes. This distribution remains the same. So randomize a set around the origin, pick a location in the mass in that set according to the mass distribution, and this holds. Well, it's, as I said, it's actually quite nice concept or definition, but it's rather mysterious. And so if we go back to this case over here, the Poisson case, what does this say? It says if we take some interval, for instance, and throw it around the origin, this is the interval, we throw it, so there is a uniformly picked point in this interval, and you place it on the origin. So you're just throwing a uniform interval around the origin. Then look into this interval, you see a point, at least this point, and maybe several others. Pick one of them at random. So maybe pick this one. Shift the origin to that one. I don't think it's obvious that the Poisson process actually remains intact by this, but it does. And so it's a curious definition, but a definition that works. But if you continue considering the Poisson process, why don't we need this concept there for the Poisson process? It's such a simple thing to define mass stationarity in this context. It's just shift to the next point on the right and nothing changes. That's sort of what I find a natural definition, but we haven't been able to implement that definition in the abstract case, in the general case of random measures. But
I understand that the thing on the left doesn't look like it has the same dimensions as the thing on the right. The thing on the right looks like some kind of triple, and the thing on the left is something with the distribution of the psi conditional.
Look at this. You take a pair and you apply a random, a group element to it. Yes, gamma here means that the origin is shifted to gamma. Down here, this means that the origin is shifted to B. Sorry. Okay, so this is just applying the group to the triple, shifting the origin for each of them. Yes.
So, in a sense, this vision that you give for the point process is very much that which you would have in the Matt's definition of the palm product. So, pick a set, go to a random point on this set,
Yes.
and locate your view from there. So, in a sense, this is another way of looking at this object you define in the same terms.
Yes, it links to the palm formula, the definition of the palm.
Of matters,
but that one uses a stationary process, and you turn it into the palm version by something like this.
Yes.
Similar, but you don't throw the interval at random. That's what sort of
You don't throw
the interval.
You pick any
fixed any set in that case.
set.
Yes.
Whereas
In this
here-
case, to cover the fact that we don't have a stationary process here, instead we randomize
on
the set.
on the set. Okay, so because the set
I think it's the same because you're actually dividing by the measure, uniform measure on this interval, so you're dividing by the local interval. I think it should be the same.
Yeah, then if you go do the calculations, you go from the palm to the stationary. That's why this works. This thing here. But okay, so
Herman, what is the third component? What does it mean? So you shift UC in this third component. What does it mean, shift? You apply VC to interval UC itself on the left.
UC is a location in the interval here, yes?
Yes, and what means you apply VC to that interval? VC.
VC to the, okay. It means that you look at this U not from the origin but from V. So it's shifting U. So this length here is U. And then you go to this
Yeah, I got it.
here, which is V, and you take U minus, yes, okay, minus V, then U.
U has a unit length, but it's uniform.
No, it's uniform on, well, take some interval. For instance, an interval of length 1 or an interval of length.
Okay, unit length doesn't matter. Yes. Fixed length.
Unit length, yes.
Fixed length.
Fixed length, yes. But you need actually to have it for all lengths.
So if instead U has a length of U has some given distribution.
U is uniform.
No, length of U. The length.
U is a uniform random variable, so, okay, you mean in 2 dimensions? No.
No, what means U? U is a
U?
random variable.
It's a random variable.
Not interval.
It's a uniform random variable. Take, for instance, in this case,
Yeah. Yes.
so UC is uniform on
Yeah. Zero.
okay.
Yes.
Is it sufficient to have just one left interval?
In the proof, yes, actually, I'm used to needing all of them, but, or an infinite, t going to infinity. But probably it's enough to have. I can't answer it now. Let's talk about it later. This is diverging from what I'm heading towards. So this. Okay, so this concept here, Mass-stationarity, is an attempt to formalize the idea that the origin is a typical location in the mass. So what is sort of mysterious here is that to me it doesn't tell me that, this shifting the origin to the next point on the right and then having the same distribution, that somehow tells me that the point that the origin is a typical location, typical point. But this really, it's just a formal definition, and there's some intuition missing there. I call it a mysterious definition, but it works for what we need it for. But so here is a theorem. The pair is mass stationary if and only if it's a palm version of a stationary pair. And for those who know palm theory, I'm actually working here with probability distribution. The P on my probability space can be sigma finite. then this theorem becomes very neat. Otherwise, you would have to assume finite intensity, positive intensity or something like that. But that's a technical thing. Okay, so it fits into palm theory in the way that it should do. A palm version of a stationary random measure is typically, people use the word, say that the origin is a typical location in the mass. I think that's a common conception, that is what the palm version gives you. And here is an attempt to give a sort of intrinsic definition without the stationary process. And it turns out to be the same concept. Okay. So what we know called mass stationarity was earlier called point stationarity, and meant exactly the kind of thing we had here. Simple point process is point stationary if it satisfies this property here. N is now a simple point process, and this pi applies to this x and n is just a shift, random shift determined by x and n. And it's a function of x and n, and this thing here should hold for all small pi having this property down here. Take a location, look at the pair from that location, apply pi, and shift by pi. Then this so-called allocation must preserve the measure n. For all pi, such that this tau preserves the measure n, this should hold. So what does this mean? It means the following: if we take pi to be so here is the origin, and take pi to be, look at the points and choose the next point on the right. So this would be pi, capital Pi. So shifting the origin to there leaves this process invariant in distribution. And so how does this tau here work? What does it mean to have this allocation tau there? Well, the allocation just takes a point and shifts it to the next point on the right. So what is it doing? It's shifting all the points to the next point on the right, and what you get, this is a mass-preserving transformation, because you map a point to a new point. When you have applied tau, you have still the same original Poisson process. Outside the points, you can just let tau sit still, be identity. You don't move when you're here. When you're at a point, go to the next on the right. When you're at a point, go to the next on the right, and you get exactly this property here. You get the Poisson process back. Okay, so this is, and I think for me this is what I wanted to have as a definition.
Hermann, I already forgot. What is x?
It's so you have some random measure and maybe a random field extra. If you don't like to have this x, throw it out. You don't need it. It's just hangs there with the random measure, and that's usually what you're interested in. You're interested in some random field, and there happens to be some random measure that helps you to study the random field. So it's really the measure that matters. Okay, so there is a definition of mass stationarity that is rather mysterious, and a definition of point stationarity that is rather transparent. And so how to, I would like to have intuitively appealing characterization of this property, mass stationarity. So what should we do? Use the Cox process. Now it enters. Okay, but it doesn't enter. There was a comment here. Okay. So this is the theorem that was added now. These three things are equivalent. N is point stationary, N is mass stationary, N is a palm version of a stationary. Okay. Okay, but now I hope enters the Cox process. Okay. A Cox process driven by this pair here is an integer valued point process which conditionally on the pair is a Poisson process with intensity measure psi. Because it's a simple point process. It means that the values of the number of points in a set is an integer.
Yeah, I understand what simple is. So you mean you may have multiple points?
Yes.
Okay.
I'm not excluding multiple points. Because if psi has a point mass,
Because on mass here, if
Yes.
it has an atom, then you have,
then you could have several points there.
well, for me it's still point process, terminology.
Oh, no, it's that's an important thing. It's an integer valued. I'm just saying it's not a simple one.
So one should call it integer valued random measure.
Random measure, yes.
Okay.
Right.
Okay.
Count is random measure.
Non-simple.
What else?
Non-simple. Not simple.
Not simple. Okay.
In what sense is it driven by x as well as by psi?
It's driven by psi, but when you know psi, x is lurking there in the background without affecting. So you have to have it conditionally on. You have to have. Should I write? It's driven by psi and conditionally independent of x giving psi. So I define driven by the pair to mean this. Okay. There is some extra stuff that it's not affecting the Cox process. It's just the random measure that is affecting the deciding on the Cox process. Okay, so this is the sort of formal definition, but I like to think of the Cox process in the following way. It represents the mass of the random measure through a collection of points placed independently and at typical locations in the mass. So now enters this n. So a point can't be out in empty space. It must be at where there is some mass. So here is a point maybe, and happens to be another one there. And here is a point and point and point and so on. And could be some point there. Wherever there is some mass in space, you could have a point, and there, if there is a point mass, you could actually have several points. These points, I think it's good to think of them as they are strewn out according to the random measure, independently of each other, and they are then placed at typical locations in the mass. Okay, so now if we, in addition, now assume that this pair is mass stationary, then the origin is a typical location in the mass. So if we now add a point here, then we get also this point is a typical location. All these points are typical locations in the mass, and this one too. So one would expect that this point process N, the modified Cox process with an extra point at the origin, it consists of typical, it consists of points at typical locations in mass, so it should be mass stationary itself. So here I'm writing what I was just saying. All these points, also the one at the origin, are now at typical locations in the mass of psi. And here is the result. It turns out that mass stationarity actually reduces to mass stationarity with respect to this Cox process. So this is the theorem. A pair is mass stationary if and only if this pair is mass stationary. So now we can think of mass stationarity through in the old way from the point of view of points. And if we
Hermann, I'm lost. Hermann.
Yes, I'm listening.
I'm lost.
Yes. So where are
Explain the theorem again.
okay. So are you lost what this theorem is saying?
Yes.
It says that if this satisfies the definition of mass stationarity, then this pair does so too. But so the idea behind this Cox process is that now we represent the mass of this maybe diffuse random measure by discrete point masses. We look at things from there, and that's enough to characterize the property of mass stationarity. So actually we could also say this pair here is a palm version of a stationary pair if and only if this one is a palm version of a stationary pair. And so in particular in the diffuse case, when psi is diffuse, then mass stationarity actually reduces all the way down to point stationarity. So we can use the definition of point stationarity, which I gave you earlier, to characterize mass stationarity, and that sort of is because the definition of point stationarity is transparent. Natural definition of the origin being a typical location in the mass. It's sort of in some sense satisfies my need to have a transparent definition, but this is not a definition. This is not at a level of definition. This is a characterization. But what can we do with this now? Yes. Yes.
Can you say that you actually change the probability space on which leads your measured psi to a new probability space, which actually carries the Cox process? So that actually instead of having realization of psi, when you say that you represent by the Cox, can you think of this way?
No, I always think of one probability space, and I am just extending it to have the Cox process there also. So there is one humongous probability space where my things are defined, and I'm just working with that one. But if you would like to map, if you map this into the canonical space, then what you say is appropriate. If you take the distribution of this thing on the space where it is defined, that's a canonical probability measure, then this guy also lives in that space, and it has another distribution, so that's you're just changing the probability measure on the canonical space. I know many people don't like this way of having a big space where you have everything you need. So if you want to get rid of that, you can just look at the image space of this pair and have the canonical space. So what you were saying applies in that case. We have some space where a pair with a, for instance, random field and a random measure is canonically defined. The value at omega is just omega itself. And there is a probability measure on that space, the distribution of this original pair here. And on the same space there is another distribution of this pair. Does it answer? Okay.
One question. When you say C is diffuse, you mean almost surely diffuse?
If you like, but I just let it be diffuse. What's the difference?
No, that's only for all omega, right? That's what you mean.
Yes. So because I'm working on a sort of convenient big probability space, I can throw out inconvenient omegas.
Make sure you don't need
Yes. Okay, so getting things down to 2 points rather than diffuse mass means that there are now lots of ways to walk in the mass of a mass-stationary random measure or of a palm version of random stationary random measure without changing the distribution. And for the last 10 years there have been many papers published on that problem, how you can shift between points of a point process, of a simple point process without changing the distribution of the process. And also you can apply now with this theorem or this corollary, you can apply the stable allocation idea of Perez and Holroyd, which gives you a way to, for instance, say we have the mass stationary pair here. Create this n. Then we have these points everywhere. Then there is a way to pick a location in space, move the origin from here down here, and we have the stationary version. For those who haven't heard about this beautiful trick, it's due to Perez and Yuval Perez and Alexander Holroyd. The idea is the following. The simplest idea, and there are many interesting versions of it now. But the simple idea is the following. So suppose you have an stationary, suppose you have a mass stationary or a point stationary point process in space. Think of those points as farmers. And we live in a good society, we want all the farmers to have the same amount of land. So model them as this point process, the mass stationary point process or point stationary point process, and allocate land to them. For simplicity, let the intensity of these points be 1. Allocate land to them by putting a little circle around each of them, or a little ball in higher dimensions, and grow these circles or balls until you have reached the mean area that each one should have, the area 1. If this ball doesn't hit another ball when it's growing, then stop when you have a unit amount of land. If it hits a land that some other point has acquired, then continue growing passively under the land until you again come into open space that no one has taken, and continue to acquire land until you in the end have amount 1 of land. This defines the partition of space in a very curious way, where this guy here might have this land like this, and then some land here, and then some land here, and then maybe some land there. And it's not good for a farmer with lots of cows to have to.
You grow spherically? I mean, you grow as a ball until you find enough land? Or?
Yes. So when land is taken and you haven't acquired your share of land, you go further out to look for it.
But they increase simultaneously.
Yes.
And on this level of generality, what prevents you for running your argument only groups? Why do you need a billion group in the first place?
What do you need? Abelian. That's.
Why a billion? You know, it's
Yes.
in general kind of.
Yes, I'm actually talking about
Group and
R2 now. I'm talking about R2 now.
no, that's
Yeah, just for an example. How do you do this in a abelian group?
Okay, Riemann volume, you know, that's the same kind of argument. I don't think you used heavily ability.
Yes, so you can actually, you need not be restricted to RD. Yes. Anyway, but the idea is clear when you think about land and farmers. So the problem with this is, of course, that the pieces of land are scattered and so on, but you can do this. And so here is this farmer at the origin, and he owns land, this part, this of unit area. Pick a location in his land uniformly at random. So, for instance, maybe you pick here. Shift the origin from here to there, and you are no longer at mass stationarity, you are at stationarity. So this is quite strong. The stationary version and its palm version live on the same space, and they have just origins at different locations. So, but this is just, I'm just pointing out that this is, of course, not new. This has been developed during the last 10 years, but I'm saying here that now we can apply the same trick to diffuse random measures by first creating the Cox process and then finding the origin of the stationary one by this trick. Okay. Thank you.
Questions left?
What do you do if you have if you do not have diffuse case?
Yes, okay, so it works also in that case. Then, if there are, say, 2 farmers at the same farm, they just grow until they have a ball of size 2.
And that's all. That's all. Yeah.
Then they have a simultaneous, and then you have to split the land between them, I guess. But it's when you have, and when you have discrete point masses, not necessarily the Cox process, but if you have when you have a point process with discrete point masses, you should look for land proportional to the size of your mass. And it also partitions space. Do you think actually it partitions space for all groups? Okay.
So you just said it's a good thing to had the point or your random measure and the palm person on the same probability space?
Say it again.
Why is it a good thing?
What is?
Why is it so good? Such a great thing to have the palm person on the same probability space as the.
Oh, it means that you can actually use almost sure arguments to prove lots of things about the two. They are the same except they have just different locations, so averages are the same, for instance.
You wouldn't know those.
So it's a coupling, really.
You wouldn't know those things without the palm.
It's a coupling. You couple the two. It's a shift coupling.
Can you also mention what kind of other types of these fair divisions of the space apart from the one you described? This is quite nasty. You have to really go very far.
Yes. So, okay, thank you. This is where, if you haven't heard about it, it's actually quite a lot that has been happening around your pairs in this business. Now there are ways to create connected areas. And rather, they also advanced in sort of getting some bounds on the diameter of the areas. But that's a rather connected.
Connected to.
So not split into pieces, but so the partition is consists of connected cells. And there is one, and since I have you here and I'm asked this question, there is one claim by Yuval and his collaborators that I still can't believe, but it's been accepted in annals of mathematics, so it has to be true. But it's tens and tens of pages of proofs and analysis that I don't master anyway. So there is a beautiful, if it is true, partition, namely the following one. It doesn't work in 2 dimensions, sadly, but they say it works in 3 dimensions and higher. So let's talk about 3 dimensions to make the picture clear. So use Newtonian gravitational force to split. So what you do is then the following. You think of the points as stars. And now they have proved this, they claim, for the Poisson process. So think of 3-dimensional space with stars at the location of a Poisson process. And then you have gravitational fields. And so if you would put a piece of a particle somewhere, it would be attracted to one of those stars, fall down into the whatever it's called, the valley of around that star. Associate to each star, to each point, Poisson point, the area that's sort of within his within the attraction in his valley. They claim, so if the intensity of the Poisson process is 1, they claim that all the cells are deterministically, or almost surely, if you like, of size 1. And that's unbelievable.
What's the allocation? You have a potential 1 over r in 3 dimensions, right?
Mm-hmm.
And what do you do with it? How do you create the cells?
I'm using the image of real space. You put a particle there, and it's going to fall down towards one of those stars. They sit.
It's going to
the solution.
No, Voronoi, because it's the sum of the mass which attracts. It's a shot. No, it's
the sum of the mass is
even infinite masses may contribute.
You do what? You let the particle move, or I don't understand.
okay. So take a location.
Being attracted by a star, and say apart from the set of 0 measure, it always being attracted by just one of the stars.
Each point in the space.
No, every particular. Yeah. Well, you have to decide what You need to create a cell. The cell is the locations of the space which are attracted by the corresponding stars.
So the weird thing here is the following. Suppose you have one star here, and then the Poisson process, it's a positive probability that there are no stars in a huge ball. So this is a possibility to have something like a single guy here, and then a huge ball around it with nothing. And they still claim that this guy only gets volume 1 of space. And they claim that the intuitive reason that they give for it is the following. There are lots of guys out here, and they sort of, they are there on the horizon, and they stretch in towards you. And so they have their long.
It's the additive nature of the gravitational field which creates this. If it were pointwise, indeed it would be the Voronoi, but it's not the Voronoi because it's essentially the additive nature of the attraction field.
Yes, the Voronoi would here, of course, be huge.
Of course, yeah. So Voronoi is known not to be exactly one for each cell. It's one in mean, but this one is one for each cell.
Am I to believe this claim, this theorem they proved? Do you think it's reasonable?
Again, what is the definition to attract? Formally, gravitation. But it's
Yes, it's
the formula. Why? What is it? At this point? So we have something.
it decays with the
Elements, and then
distance
they have
squared.
stars. So
What it decays with the distance squared.
yeah.
Yes, and then you sum up all these, what is it called, potentials or
The
whatever.
potential is 1 over r. The field is 1 over r squared.
Okay.
If you condition,
Yes, yes.
if you condition on all the points, then of course this should not be true. So there's some kind of averaging that is.
You can't condition on all the points
Yes.
because that's a null set. Yes.
So what's the averaging that's going on? Can you say something?
It's somehow you can't get the Poisson guys, even if you do this, don't allow them to be in a huge ball. You can't organize them in enough detail to destroy this property. It's absolutely counterintuitive for me, at least.
If I put finitely many points on a sphere, on a two-dimensional sphere, and apply this gravitational law, I mean, it'd be interesting to see. Because then you can condition on the points.
Two-dimensional sphere. Yes,
Two-dimensional
yes.
sphere.
Yes.
And you put the points. Of course, maybe you need the three-dimensional sphere embedded in four-dimensional.
They have their simulations of this. Go on the web, and they have these simulations.
Well, because I'm trying to say you put on a compact manifold and
Yes, okay.
Newtonian potential sphere, so you can condition. I don't know. That's a natural thing to do.
To prove this or disprove.
To see what it means, just to I don't know whatever. So in 2 dimensions it doesn't work.
In 2 dimensions, it doesn't work.
Logarithms.
Yes, that's because of the.
And it's only for Poisson process, right?
They proved this for the Poisson
Yeah,
process.
that's why I said you cannot take a uniform number of points over the whole space, but you can take a uniform number of points on the sphere, and then randomize, make a Poisson distribution on this. So take condition first. Poisson distribution, condition, the value. I put uniform. I don't quite understand.
And somehow things happen at infinity that you can't control. And it affects you here.
Yeah.